second lesson, we're going to be working with optimization problems today. Your book refers to them as minima and maxima problems. And our goal is today to figure out how large something can be to satisfy some criteria, or how small it has to be to satisfy some criteria. And we're going to look at it through two examples. Let's take a look at the first one, which is a maximization problem. So what we're going to look at right now is how do we use maximum and minimum to find optimal conditions. So that's our aim right up here. These are called optimization problems. We're given some starting condition and we need to find the biggest water tank, the biggest area of a field, something along those lines given our starting conditions. And here we have a pretty standard example. You might want to pause and write it in. Farmer has 2,400 feet of fencing to fence off a rectangular field that borders a river. He needs no fence along the river. Apparently something can't escape that way. What are the dimensions of the field that has the largest area? Now, you could try to do a lot of guess and check here. It's not going to be very helpful. And in fact, we have calculus, so we can avoid doing that. And what we're going to have to do is set up two different equations. So we know if we're looking at this that it's a rectangle. This is, let's call this x, let's call this x. They have to be the same because it's a rectangle. And let's call this distance y. Now, we have two equations we can make out of this. The area is going to have to just be x times y. Area of a rectangle. But the other equation that we can say is that 2,400 is equal to 2x plus y. The 2,400 came from the fact that he has 2,400 feet of fencing, and 2x plus y has to add up to 2,400. We're going to first make our area problem into a one-variable problem. So we know that I can switch y out, so I'm just left with x. That means that the area is just going to be left with x times 2,400 minus 2x. I did that just by switching out y. And that's just going to give 2,400 2x squared. So, what are we going to do now? Well, same thing we did before. We're going to find the derivative. So, a prime, well, that's not too difficult. 2,400, I should put a plus there, plus 4x. That's our derivative. Cool, easy peasy. What we need to do now is set this equal to 0 and solve for a maximum. Well, that's going to be pretty easy. 2,400 is going to equal negative 4x, and we're going to get x equals 600. Oh, excuse me, this should be a minus, that should be a minus, that should be a plus. That's how we get a positive number. Yay. How does this help us find our area? Well, you just plug this in, same as we found the critical points in our last lesson. And we say, well, a is equal to 600 times 2,400 minus 2 times 600. That's going to give us our largest area of that. And now we know that x has to equal 600 because they did ask us for the dimensions, so we need to actually find our dimensions. X is 600, and y I can use this part for. It's just going to be 2,400 minus 2 times 600. That's going to be 1,200. So the dimensions which we want, x is going to be 600, y is going to be 2,400. That'll give us our largest area. Now, what you can also do besides solving for where the derivative is equal to 0 is just plug the derivative into anything that can graph and see where the maximum or minimum is. In the last problem, it would be where the maximum is. We're going to take a look at why you can't always do that in our second problem, where it's going to be a minimization problem. Our minimum is at a very uncomfortable number that you can't easily pick up. And if you estimate, your other answers won't be as exact and they won't be as pretty. We'll see this one actually gives a very elegant answer towards the end of it. So let's try a second one. This is going to be a minimization problem. We're trying to find the smallest possible value. The reason being is we have a can that's meant to hold a liter of oil, and we want to use as little metal as humanly possible. So a really very real-world application. The two equations we're going to use, we're going to have one equation for the surface area, and that's just going to be 2 pi r squared plus 2 pi r h. The 2 pi r squared, that's two circles, so the area of the top of the can and the bottom of the can. This area represents the sides of the can. The 2 pi r is the circumference of a circle, the h is the height. So this is kind of like if you took the label off a can, it would be a rectangle. And these are the two circles. Together they make the entire surface area. Now we know we need a second equation with these problems in order to get into one variable, just like it says in your textbook, which of course you've all read by this point. And we can use the volume of a cylinder formula. We know it's this. Well, we need to find the volume. Here, the metric system helps us out. The liter that this is supposed to hold is 1,000 cubic centimeters. That means we can solve for h, and h is just going to be 1,000 divided by pi r squared, which means I can plug h up here, and it'll now be replaced by constant r, which is really helpful. So that means that the area is going to be 2 pi r squared plus 2 pi r 1,000 over pi r squared. And if we simplify that a bit more just to make our math and our lives easier, we're just going to wind up with this. So we want to minimize this. If you graph it out, we're really only concerned about the positive values of r here because, well, we can't have a negative value of r in the real world. So let's find our derivative. So that's just going to be, well, 4 pi r from this first part because 2 and pi are just constants. And it's going to be minus 2,000 over r squared. Cool. La da 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 da. If we wanted to, we could simplify this a little bit. We could, well, not simplify, that's the wrong term for it. We can combine everything together. If you're wondering about the algebra behind it, well, try to figure it out on your own. Now, what we need to do here, set it equal to 0 and solve it out. Well, we can definitely do that. So, 4 pi r cubed minus 500 over r squared equals 0. And it turns out that we're going to get this when equals 500. That doesn't look like a very satisfying number. However, considering our answer is going to be 500 divided by pi, all to the cubed root, I don't want to figure out that number because that's just, quite frankly, awful. Now, we need to find the dimensions here. We found the radius, now we need to figure out our height. We know that this is our height formula. So I'm going to take this, I'm going to plug it in. So I know that h is going to be equal to 1,000 divided by pi r squared. Well, we knew that. So now it's going to just be 1,000 divided by all of this, 500 over pi, now to the 2/3 power. And if we simplify that a bit more, it's actually going to simplify down to 2r. Now, that actually happens a fair amount in these problems. It simplifies down to something which looks elegant and simple, and it's actually really cool. So you just saw two examples, plus you read the two from your book. You're going to go ahead and give your homework a shot. Remember, follow the steps that are in your book for this. They are on 387. Making a sketch. You're writing an equation that you want to maximize or minimize. You're getting into one variable. You're using a grapher or a plotter in order to figure out what the maximum or minimum might be. You're solving by setting the derivative equal to 0. And then, and I can't stress this enough, please make sure you're actually finding what the question is asking for. After that, give the stated homework a chance and you're good to go. So remember, please post any questions that you have to this assignment or see me during office hours. Hope everything is well, folks, and I will talk at you soon. Bye.